Next up, please welcome Gadget, who will tell us something about Eyes for Robots.
Hi, good evening, everybody. How's everybody doing? My name is Tom Erciani. Some of you might know me as Mr. Gadget. Thank you so much. Short introduction, who am I? I'm a roboticist. I love building robots. Competed in a few competitions. I work as a technology specialist, whatever that means, at a Swiss company. And I love to build stuff. So you might have noticed the big ass video wall that we have in the makerspace. And yeah, today we're going to talk about robots, because robots, well, they're basically everywhere. They're underwater, they're on the water, they're on the land. I mean, we see Teslas, we see robots that deliver packets, that deliver passengers. We even send some to different planets, and of course, drones. So right now, everyone can own a drone. But we live in exciting times. We went from actual science fiction to science fact. So, wait, here. So the play, yeah. So, what? Black magic, yes, of course. Black magic and cats and Roombas. So a few decades ago, like the Terminator movie was like, yeah, the science fiction movie. And if we look like at current technology, we're quite close to what was depicted there. And building robots is hard. So we didn't get there from one day to another. There was a lot of this in between. So this is actually from the DARPA Robotics Challenge. I think the title of that video is "Robots Might Be Just Drunk People." So building robots is the easy part. Actually, let the robot do what you intended to do is actually the really, really tricky part. So they all actually share the same problem. Navigation. So what is navigation? It's the process or activity of accurately ascertaining one's position and planning and following a route, according to Google. So we know different ways of navigation. So we use everyday technologies like GPS, we use LiDAR, we use inertial measurement units. So we got that in the hand, so in the cell phones. We got sonar, we got radar, and we got computer vision. So each and every technology has its ups and downs. So GPS is very, very cheap to get these days. It's basically free, and you get global coverage, or mostly global coverage. But for robotics, just relying on GPS, consumer-grade receivers, they're not accurate enough. So, and they need line of sight. So, ever try to navigate by phone inside of a building? It kind of sucks. So, LiDAR uses lasers. This is pretty awesome technology. It's super fast, it's accurate, their range is fantastic, but it's expensive. And the generated data is massive, so you actually need a lot of processing power to actually make something useful out of that data. And then we have inertial measurement units. They're pretty cheap. The data acquisition is super fast, but they drift over time. And if you want to know more about IMU navigation, you should see this guy's talk from last year's Balkan, Dancing in the Dark, where he actually explains why IMUs are like they are. And then we have computer vision. It's pretty cheap to start off. You can spend a lot of money in computer vision regarding hardware, but it's pretty robust. It works indoors and outdoors, depending on the camera that you use. And again, the accuracy is depending on the amount of hardware and processing power that you actually have. Here, the same problem with LiDAR. It can generate a lot of data. So, what kind of sensors are there? So, I'm going to talk about three different kinds of sensors. So we got stereoscopic, monoscopic, and structured light. So what is a stereoscopic sensor? So it's basically two cameras, like we got in our eyes, like with our eyes, and we can extract three-dimensional information by comparing two images. So, well, how do we perceive three-dimensional work? So if you put your finger very close to your face and you close one eye after the other, you will notice that the finger will jump a lot between the two eyes. And if you focus on a point that's far further away, it probably won't jump at all. And this is basically what we're trying to replicate with stereo sensors. So yeah, we have stereo sensors too. And this is how we do it. So we compare different points and different images to actually try to calculate how far is that point in space. And it looks something like that. So to explain the overview, so we have what we actually see in a 2D image. In the lower part, we see what the depth calculation looks like. And on the right part, we actually see the combination of both of them. All right, so this is good, but yeah, what can we do with it? Well, for now, all right, let's talk about features. How do we know that these pictures belong together? So if we look at them, for us, it's pretty obvious. They might be in the same spot. So the same thing goes for robots. So we try to find so-called features in pictures and try to find them in the next image. And this is how we can actually tell, or the robot can tell, that yeah, these pictures belong together. But something crucial that we have to keep in mind. Navigation or image processing is highly reliable on image quality. Whoever got up at night and didn't turn on the lights and actually knew where he was and bumped his foot anyways. So even us, we're relying on it. And I mean, reoccurring patterns is pretty confusing if we saw them before. I mean, everyone got lost at some point because everything looked the same. So these are the problems that can arise if we don't have context, if we don't have previous information of where we are right now. And the same goes for how we can determine those features. I mean, if we're just looking at the white wall, it's pretty hard to compare it to the next white wall. And movement, again, is crucial. If we can't process it fast enough between images, it will just generate nonsense. So we got those features. Awesome. If we save those features, if we save the information of the features, what do we get? Exactly, a map. And creating a map is crucial for us too. So the first time that we go to a place and we don't know it, we have to notice, okay, where is what? That's only the first time. So it's computationally intense. But as soon as we got a hold of your surroundings, we're pretty much good. Opening a new door, we don't have to rethink how the whole venue looks. We just add it to the map. So we can actually share the map that we generate as humans with others. I can explain to you how to get to the bar next door. I don't have to tell you what color the floor looks like. I can tell you, go through that door, turn left, and then straight ahead. So having a data doesn't need necessarily a lot of data. It has to be the right data, and the right data is actually a pretty complex part. When generating a data, we differentiate between two different methods. So we talk about online and offline. What does online and offline mean? So online means, let's say we have a moving platform, and we actually generate the data, the map, on the platform itself. So you can imagine it has its pros and cons. The con is we need a lot of processing power on the moving platform. But we can actually extend and adjust the map on the fly. And offline is you drive through a venue, you drive through an area, you copy that data to a more powerful machine, and then you run it through and through and through, and you get very accurate data. So online, to summarize, we need good processing power, or good enough, whatever that means, depending on the cameras that you use. And mostly it's a trade-off in map quality. So you can't expect to get the same exact quality of map than the offline, because we can actually rematch and rerun it and all over again. But things like moving people can be reduced or removed from the existing map that we do in an online run. But the online, yeah, you can record the data with a pretty low-tech device and then copy it to a machine that actually has the processing power like a GPU, and just refeed that generated map data to your moving platform. But why not use both of them? So you can actually do a first run with a lower resolution quality and saving all that data, and then copy it to like a powerful desktop and reuse that all over again. This could look something like this. So I'm going to use what I'm using here is a software called RTAB Map. So it's real-time appearance-based mapping combined with a nifty little stereo camera. And does it work? It should. Let's see. All right, yes, we're running. All right, so we see the first frame that we saw in the earlier video, and we actually attach each and every one with the previously known position. And like that, we can actually generate pretty good data. And we can relocalize ourselves. So if we as humans, if we find ourselves in a place that we already know, we take a look around and we see if we recognize things. Best thing is to see actually a sign. So, oh, you're on the first floor. Awesome, I know where I am, so I know where I want to go. And after we've done like that first initial run, we can copy it to a more powerful machine and actually have the whole map generated in a kind of a better resolution. Let's see. All right, so these are stereo sensors. Pretty awesome. All right, what are monoscopic sensors? Well, it's basically one camera. That's it. But we reduce like the amount of data that we generate by half, which means we don't have to have that much processing power, but it's kind of more difficult to use to map an area and to estimate like an object's position in space is not that trivial without a few tricks. All right, let's do a little experiment. Can someone tell me how big that zebra is? Like, how big is it? Is it like 2 meters? That? Like that? That? All right, try again. How big is that zebra? Yeah? All right, so why is it easier to tell the size of that zebra? Exactly. We have an object that we know the exact size of it, and that's the same thing that we're going to do that we can do with computer vision. So
it's a giant CD.
yeah, if it's a giant CD, something like that happens. So we actually, if we don't have a correct like size reference, humans can get screwed too. Thanks for the question. Perfect. All right, so what we do with robotics, we actually use something called markers. So we pre-program or we tell the robot that this tag has a set size. So if we see them in a picture, so we can actually calculate the size of that tag according to the pixels that it takes on the image. And if we see multiple ones, we can actually use that to localize ourselves, which looks something like this. So you see we can actually get the orientation of those tags. And on the right side, we see like a map that we generate with the location of those tags. And it's not necessarily just in a two-dimensional space. We can use that in a three-dimensional space. Now, this is kind of cheating because usually you don't have the luxury of tags in an area that you operate. If you have the chance, of course, it makes stuff easier. But this helps to kind of get a simple localization method with relatively low-tech equipment. And you see the three-dimensional placement of those tags. But so how do we handle monoscopic vision? How do we determine like if a certain what's distance of a certain point? So if you close your eyes and try to estimate point in space with one eye closed, just without moving, it's kind of hard. So what do? We actually move slightly left and right and try to actually reach or calculate the position of that. So movement helps us, and we handle monovision just fine. There are people that manage actually pretty good. So 3D with just one eye, awesome, yay. Well, yes, but actually no. Because our body cheats, we use all our senses to actually combined to actually get that depth information of a certain point in space. So we use our hearing, we use our eyes, we use our touch. So again, the example with getting out at night and bumping your feet. Your feet are actually like bumpers on a Roomba, so it tells you to stop. We take our feet, and all that gets combined in that computing thingy in our head, which helps us navigate. We do the same with robots. So we might replace the sense of hearing with sonar, replace the eyes obviously with cameras, bumpers as tactile input, and we use wheels to get a sense how much did we move in space. So we can actually combine those and get a more robust localization method, because what we're trying to do is actually eliminate the errors of all the other sensors. And we can actually do that too with computer vision. So this is a short video that I made. So I used my smartphone with an AR framework, some Unity game engine. So it's pretty much a copy-paste method. But we see here the white surface represents the floor, so it detects the floor. And when we move, it actually tries to match those pixels to the previous frame. And in the top, it might be hard to see, but we actually see the distance that we walked, and now we see the different steps on that get detected as a plane. And if we turn around at some point here, we actually can log where we went and see our path that we did. And this was just used, this was just with a smartphone. All right. Well, it's a pretty powerful smartphone. The smartphones that you carry today, they pack quite a lot of processing power. All right, so let's talk about structured light. The structured light can be used with one camera or two cameras, but it adds projector to it. That mostly it's infrared laser that projects a known pattern on a surface. And by the deformation of that pattern, we can actually calculate or estimate the surface of an object, or a three-dimensional surface. So how does that look? This is like the example video from Intel. So you actually see the different patterns that get projected on that person, and by analyzing the deformation of the different lines, we can get a pretty good estimate of the surface of that object. We can use points too. So In here you see like those different IR points that we don't see in an RGB image, obviously. And this helps us to get a better feeling for the depth. But structured light, they have their ups and downs, so it's pretty good in getting better three-dimensional data. And usually the accuracy is much better, but they're pretty susceptible to like external noise. So sunlight is pretty much a killer for it. So you can't really use it or it's hard to use it in an outdoor situation. But all those camera technologies can be used in different ways. So we can use them to give an operator of a remote vehicle like a sense of depth in the case of stereo cameras. I mean, anybody like has done some drone flying, some first-person drone flying. It's pretty hard to determine like the depth or get a feeling for the size of objects if you're flying just with a simple camera. It needs a lot of experience, and you need to fly around, and you probably crash a lot. So that could be used for let's say a person that operates a robot that inspects like a nuclear power plant that gets used in a bomb diffusal situation where it's really hard for the guys that operate those vehicles to get a hold of what is in front of them. So I know for the bomb diffusal robots, what they do, sometimes they put like a 10 centimeter long strip in front of the camera so they actually can see it, and they get closer to the object until they see that the paper actually moves. And having like a stereo camera, you can actually wear, let's say, a VR headset and have a sense of depth, which is actually really useful. And of course, autonomous cars. A lot of autonomous cars these days, they combine different sensors. And I think Tesla is heavily invested into vision-based navigation. So this is pretty cool, but let's talk a bit hardware. One of my favorite ones is the Z Mini, which is this guy over here. It's pretty tiny. It has a built-in IMU, so it actually registers your movement, which can be used in combination with the images that you get to get a more robust tracking. Awesome. We got the RealSense camera, which is this little guy over here. This is actually a structured light sensor that has an infrared projector on it. Stereo camera, it is kind of finicky, so not really my favorite. But a newer one is actually one of Intel RealSense. Well, I have a lot of Intel products because they have quite a few of those. This sensor is pretty cool because it does most of the computation, position estimation on board. So you can use that with a pretty low-powered system and actually just stream the position data right back to your computer. But those cameras you might have seen are pretty expensive, and for people that want to start with computer vision, this can be overwhelming. So meet the Je vois camera. So Je vois means I see in French. It's this little tiny camera, and if I talk tiny, I mean this is the camera. So it does all the computer vision on board. So you actually have a micro SD card that runs a full Linux. Attach it via USB to your host computer, and it just gets registered as a webcam. So no special drivers needed. It's pretty. It's powerful enough to do some amazing things. It's open source. And it was developed by the University of Southern California, actually with the intention to provide a platform for students to start with computer vision. They made a Kickstarter campaign out of it, and I thought it was pretty cool, so I was one of those the backers. And the whole platform is really well documented. You have a lot of examples from machine learning, let's say object recognition, to tracker recognition, facial recognition, iris tracking, and depending on what you want to do, it's fast enough. But you don't really necessarily need to be limited to external hardware. You can actually use your laptop's webcam, or actually any USB webcam, to get you started. So, software, that's usually where the problem lies. You can't really do computer vision without once using OpenCV. So it's the open source computer vision framework. It's cross-form compatible. It brings like a load of features. Most of the image processing stuff that you see online is actually at some point related to OpenCV, and it is well documented, and you find a lot of YouTube tutorials online. So kind of a fun project is OpenPose. So this project aims to actually detect humans in a 2D image, and actually assigning skeletons to the different body parts, which looks something like this. They use like machine learning to train the framework how humans would look like in a picture. This is quite cool. So Facebook just recently released like the upgraded version of that, which is called DensePose, and it can actually reconstruct like surfaces of humans in a 2D image, which looks something like this, which is pretty scary. And probably if you're into like machine learning, you won't get around TensorFlow, which is the open source library of Google. Again, this too is pretty well documented, and you get fantastic tutorials to start your journey into like computer vision. So what lies in the future? All right, I think robots will more and more be used in certain fields like disaster relief, so that you actually send out swarms that would actually gather data to detect victims of, let's say, an earthquake, to 3D map a certain area and get like a situational awareness of what's going on, to deliver. Drones are already used to deliver blood bags in remote areas in Africa. So I think that there will be a lot of change in that area. And of course, medicine. Using computer vision in medicines brings like a lot of potential, because machines are really good in recognizing patterns. You just have to teach them which patterns are actually interesting. So I think this can be used combined with machine learning to actually give doctors an additional sense for what they're looking at, because not every doctor is equally trained to interpret data that he's looking at. Let's, for example, say an EKG, like measurement of your heart. There are like subtle differences that not all doctors are equally trained for, and not all of them can actually recognize those patterns. Patient monitoring. We're talking about robots that actually can allow elderly people to stay in their home instead of having to put them in an elderly home, and for experts to have the ability to actually remotely log in and actually inspect the patient, something like that. Of course, we have autonomous vehicles. Those will come. And they will have a bunch of sensors in them. If you want to see what can go wrong with sensors and autonomous vehicles, I'd highly suggest Zos's talk last year about hacking autonomous vehicles. But this is not all. We're talking surveillance. The computer vision, especially machine learning, enables, let's say, state actors to use that technology to do a large-scale surveillance without the need of humans to actually classify it. And of course, warfare. So it has its ups and downs, but I would like to focus on the good things. So yeah, to like do a short recap, we have stereo vision, we have mono vision. and vision that uses structured light to actually estimate its three-dimensional environment. And yeah, and I would suggest be nice to your robots because we might work one day for them. And with that, I'll be open for questions if you have some. Yes.
Hi, Domer. Thank you very much for this talk. I have one question. What do you think about the statement that Elon Musk gave that we don't need LiDAR for autonomous driving and for self-driving cars?
I would partially agree. LiDAR is good in certain areas, but I think if you want to scale it up, machine vision should be used as a main sensor. But again, machine vision has its weaknesses. So let's say fog, or if there's dirt on the cameras. So I would suggest not to rely on only one sensor, but actually use maybe a radar as an additional one. And I don't think LiDAR is a necessity for autonomous vehicles. It certainly helps, and it looks cool to actually generate this point cloud. All right.
You mentioned that the better the quality of the image, the better we can get information from that data, but then you're talking about more structured, more complex kernels and neural networks. So you're talking about more computational power to analyze more data, more pixels. Do you think it's that there's some form of limit where we can say this is enough information, but we could use more processing power to just get more calculations out of that pattern? Or do you think it's just better and better to keep going with the pixel counts and everything?
Yeah, it depends. I had a similar discussion just a few days ago. So moving from, let's say, 720p to 8K image resolution, most of the time you won't gain a lot of information compared to the lower resolution. So it's always like the question, what do you want to use it for, and what's good enough? Because at some point, computational power gets more and more, it gets cheaper every day, right? So we tend to raise the amount of data that we feed in, but yeah, it always depends what's the given constraint, what's the limiting factor of the project that you use, and usually it's a good idea to lower the resolution and sacrifice lower resolution for higher frame rate. If that answers your question. All right. Thank you very much.